Have you ever just looked up at the sky or watched a massive ship glide across the water and just wondered? How does it all work? Well, there are these incredible, invisible forces all around us, shaping everything. And today, we're going to make those invisible forces visible. We're diving deep into the fascinating world of fluid mechanics.
I mean, think about it for a second. These are huge questions, right? How does a massive steel ship weighing billions of tons just float so effortlessly? How can a 500-ton airplane climb into the clouds and just hang there? What's the secret sauce that connects a floating boat, a flying plane, and even the way a river carves its path through the land?
Well, believe it or not, there is a common thread, and that thread is fluid mechanics. It's this hidden science that engineers and physicists use to understand, predict, and control all the liquids and gases that shape our reality. This is our key to unlocking all those mysteries.
So, let's start right at the beginning. What exactly is this incredibly powerful science?
Okay, so at its core, fluid mechanics is the science of how fluids behave. Simple enough, right? That could be water just sitting still in a glass. That's called fluid statics. Or it could be the wind whipping through a storm, which is fluid dynamics. But here's the crucial part. It also covers how those fluids interact with solid objects. Think air pushing against an airplane wing.
Now, when I say the word fluid, your brain probably jumps straight to water. And that's fair, but the term is actually way broader than that. So what really counts as a fluid? And this slide shows the two main types perfectly. On the left, you've got a liquid. See how it takes the shape of the bottom of the container, but it has that distinct top surface? But then on the right, you have a gas. Its molecules are just so energetic that they expand and fill every single nook and cranny of the container. Both of them, liquids and gases, are fluids. So here's the really scientific heart of it. Unlike a solid, which can resist a force and hold its shape, a fluid just can't. If you give it even the slightest sideways push, that's what shear stress is, it'll just start moving and keep on moving. It continuously deforms. It just goes with the flow, literally. That's what defines a fluid.
Okay, but here's where it gets really cool. Not all fluid motion is the same. It can be incredibly smooth and orderly, or it can be completely wild and chaotic. Let's take a look at the two very different faces of fluid flow. First up, we have what's called laminar flow. Just look at how smooth and organized those layers are. This is what you see when you pour something thick like honey or oil. The fluid moves in these neat, parallel sheets that just slide past each other so gracefully. It's predictable, it's smooth, it's laminar. But then, as things start to speed up, you hit this weird, unstable middle ground called transitional flow. You can see how those nice, neat layers are starting to get all wavy and begin to break down. This is where chaos starts to creep in, and the flow just can't decide if it wants to be smooth or disorderly. And finally, you get this, turbulent flow. This is the complete opposite of laminar. It's chaotic, it's disordered, and it's jam-packed with all these random swirls and eddies. Think of a raging river or the air rushing past a car on the highway. Fun fact, most of the fluid flows we deal with in everyday life are actually turbulent. So that's the million-dollar question for any engineer, isn't it? How in the world do you know what kind of flow you're going to get? How can you predict if it's going to be smooth and orderly or just totally wild? Well, thankfully, we have a really powerful tool that helps us do exactly that. It's called the Reynolds number. And it sounds complicated, but the idea is actually brilliant. It's basically a simple calculation that compares two competing forces. You've got inertia, which is the fluid's tendency to just keep plowing ahead in a straight line. And you've got viscosity, which is the fluid's internal friction, its stickiness, that tries to calm things down. The winner of that tug of war determines everything.
And this analogy just makes it crystal clear. Think about a huge truck speeding on an icy road. It has tons of momentum. That's high inertia, but almost no stopping force or low viscosity from the ice. It's a totally unstable, chaotic situation, right? That is exactly like a turbulent flow with a high Reynolds number. A low Reynolds number is the opposite, like someone walking slowly on dry pavement. Totally stable, orderly, and very laminar.
Okay, so now that we've got a handle on the different types of flow, let's go back and tackle one of those big questions from the beginning. How do airplanes actually fly? The secret is in this fascinating, kind of weird relationship between a fluid's speed and its pressure.
This is the famous Bernoulli's principle, and it can feel a little counterintuitive at first, but it is so important. All it says is this: where a fluid is moving fast, its pressure is low, and where it's moving slow, its pressure is high. That's it. Fast flow equals low pressure, slow flow equals high pressure. Just burn that into your brain. So how does that make a plane fly? Well, an airplane wing is specially shaped to be curved on top. Because of that curve, the air has to travel a longer path over the top than it does underneath. And to cover that longer distance in the same amount of time, the air on top has to move faster. And what did we just learn? Faster air means lower pressure. So you end up with low pressure on top of the wing and higher pressure on the bottom. And that pressure difference creates a net upward force. We call that force lift. You know, understanding these principles of flow and pressure isn't just some academic exercise. It is the absolute foundation of so much of our modern world. Let's just look at a few ways it's engineered into our daily lives. Take your car, for instance. Engineers spend thousands of hours in wind tunnels, carefully shaping every car's body to manage that turbulent air flowing over it. By making the flow smoother, they reduce drag. Less drag means the engine doesn't have to work as hard, which saves you fuel and makes the car safer and more stable at high speeds. And look at this. The blades of a wind turbine, they're basically just airplane wings stood on their end. They're designed with the perfect aerodynamic shape to maximize the force of lift they can get from the wind. They're literally turning that lift force into clean, renewable electricity. Even the pipes that are hidden in our walls and running under our cities are these incredible feats of fluid mechanics. Engineers have to perfectly balance pressure, flow rate, and viscosity to make sure everything from our drinking water to natural gas gets exactly where it needs to go safely and efficiently without wasting energy. And get this, the applications even go inside our own bodies. When you're designing an artificial heart, you need an incredibly deep understanding of how blood, which is a very complex fluid, actually flows. If you get that flow wrong, you can create turbulence that causes blood clots, so getting it right is literally a matter of life and death. So, as we wrap all this up, what's the one big thing you should really take away from our little journey today? It's that this science is truly, genuinely everywhere. It's not just about fancy planes and fast cars. It's in the massive ocean currents that regulate our planet's climate. It's in the weather patterns you see on the news every night. It is literally in the blood flowing through your veins as we speak. Fluid mechanics is the hidden language of a world that is in constant motion. And now, you know how to read a few of its words.